So I'm gonna talk today about the DiPaCo, so our distributed path composition. It's a prototype, so I'm not saying this will be replacing all the current LLM or anything. It's only a prototype, but it's in a radical different way, I think, to do distributed training, which has been my current topic of interest for more than 1 or 2 years. As every project, it's not only my project, it's the project of the team. It was a lot of engineering. We actually did distributed training for real, so it was not a toy model. We did it across continents at a relatively large scale, which require a lot of work, both engineering and science. So just I want to thank all my coworkers here. Our goal is to train a network in collaboration across the whole world. So similar, I think, to what Yosh said, we would like to be able to make the AI more collaborative. So right now it's a few labs, so Anthropic, Cohere, DeepMind, OpenAI, who train in a data center, usually one single data center in a single location, and you train a big network and that's it. But what if you want to train a collaboration? So that collaboration could be internal, even just Google a data center across the world with different researchers. So we could collaborate across all data centers of Google, but also in a broader cost. You could see that different universities have few GPUs, but they may want to collaborate with all other universities and pull together all their compute. So for that, that's our main vision. But we want also to scale efficiently. There is the bitter lesson that basically scaling your model and your model size, or at least the number of flops, seems to be better. So we need to go in that direction. We need to scale more efficiently. But we want to do it quite smartly. We don't want to scale the model size and its number of flops linearly, as at some point we won't be able to feed the model. And it's even more important at test time. So we know there are sometimes some models that are particularly hard, that are very good, but they're hard to serve. We don't want that, especially in the context of like collaboration across the world, because probably a university won't be able to serve a big model. So we want to be able, everyone, even on maybe on a local small laptop, could serve a model. And furthermore, I'm talking about distributed and collaboration, meaning that it's going to have a lot more of compute that is quite unreliable, especially if you work with compute managed by different people. So we want to be resilient to hardware failure, heterogeneous accelerators, because not all universities, for example, will have the same kind of GPU. So what if we could actually pull together a different kind of GPU? That would be awesome. And also short-lived compute pools. So whether you use pools that can be preempted, or maybe some GPU are sometimes used by someone else, so you cannot access it to the pool or anything, we want to be able to resize our compute pool on the fly, dynamically. So that's our big vision. To simplify, we have two big building blocks. The first one is coarse routing of entire examples to expect. The second one is a low communication distributed training optimizer. So what is coarse routing? In practice, routing is something you may be familiar if you're familiar with, for example, Mixture of Experts. In Mixture of Experts, you have an online router who takes tokens, and it's just a linear classifier, and then say, oh, this token must go to this expert or this to this expert, and etc. But this is a per token routing. So each token is given a decision of which expert to go. A coarse routing here, we're going to do a routing at the seconds level. So to do so, we need to first start with some kind of set of embeddings. I don't think the set embeddings or the quality of those embeddings matter much. We use those embeddings to pre-shard our dataset into K shards using k-means. We could use more fancy clustering methods, but k-means already work quite well for that task. And we're going to do a sequence level routing, as I said, in the context of language modeling. So here we are pre-sharding datasets with 4 kind of clustering. We could also use other information, so not simply k-means, but we could maybe use some metadata if we want to start it. Then we're going to associate for each dataset an expert, or here in the case we call it a path. A path, an expert here, is an entire model, a whole LLM that could be relatively large. In that case, our path, each path is of 150 million parameters. So we have one expert per data shard. And then, as an example, what we call the flat mixture, we can train independently each path, each model, independently on different kind of hardware, different kind of location, and we can train them on each of them on their own datasets. So, for example, we can find that one dataset will be specialized for code, one for languages, one for reasoning, for example, and you will have different kind of experts that are very specialized for each kind of data shard. And at test time, how do we do? at test time, we could simply use our coming routers to select the optimal path. So for example, we know that at test time, I'm writing a text that requires, for example, language skills. It selects the dataset 2, we select the path 2, and we forward to that path to get our new generation. This course routing of seconds to expert has two big advantages during training because there is no communication at all between each path. So in a classical mixture of experts, all experts are actually tightly synchronized. In that case, not at all, because we do the pre-sharding offline before the training, and then you can pre-shard the datasets on different locations across the world where there is each of the path, and then you have perfect parallelism. So that's great. And you also, another advantage, an extreme specialization per expert. We know that some kind of specialization for a model is actually very useful. You know that if you want to use, for example, an LLM to help you for coding, you're probably not going to take whatever LLM, Gemini or GPT out of the box, but you're going to probably use a version that has been fine-tuned for the code that will be slightly better on that task. So extreme specialization of an LLM is actually very useful. The course routing of seconds to expert has a big drawback. We don't have any knowledge sharing. Indeed, you route a whole sequence, so that could be here in the context of a chatbot, for example, a conversation. You route the whole conversation to a single expert, which is great, for example, if I route my conversation to an expert that do math, if I want to ask math. But let's say I want to do, for example, math in Spanish. The problem is I will probably have an expert for Spanish, an expert for math, but actually I have to choose between the two experts, and there is no knowledge sharing between those two, which is not what we want. So there is a solution. It is that at test time, we can actually do a frequent gating. So at train time, as I said before, we do a gating of per seconds. So this gating, basically, we take the first few tokens, 32 tokens, for example, of our seconds, we extract the embedding, and we go to our gator, which is k-mean clustering. We know that, for example, here we need to select the path 2. So then we can train our whole path 2 on that sequence. That's the training time that I explained before. Then at test time, we can do something similar. So we first start with our prefix. So that could be, for example, the initial text that you send to a chatbot. You go through the gator, you select then the path 1, and then you do a scoring or sampling of the next chunk. And then you can see that maybe during the conversation, you alternate between the user and the chatbot. And regularly, we could take, for example, the next chunk, either from the chatbot or from the user, and you can combine it. You can give it again to the gator here, and we select the path 4. Meaning that basically, it's not the perfect knowledge sharing, of course, but it allows you actually to combine and interleave in the same sequence multiple kind of experts. Which is already something that everyone is kind of doing it. So if you know speculative decoding, for example, in speculative decoding, it's a way to accelerate the training. You have a small LLM that generates a lot of tokens, and then a bigger LLM, better but slower, who actually scoring, and then sometimes rewrite. So there's already some kind of knowledge sharing at a very coarse granularity. In that case, that's quite similar. The big drawback of our method, unfortunately, that we don't solve yet in this paper, is that we need to recompute the Kali cache. So indeed, for those who don't know, when you do sampling at test time, you're going to sample tokens per tokens, and you don't want to recompute all the embeddings, all the intermediary activation of the previous token. Therefore, you store those values, only the values for the K and the value, the Kali cache. In that case, because we switch LLM, for example, between each chunk, you will need to recompute this Kali cache. However, it is not as costly as it looks like because it's a single forward pass, while during the inference, during the sampling, it's actually more costly workload time to generate tokens per tokens, the distributed part of DiPaCo. So for that, we need a low communication distributed training optimizer. So just for a quick reminder, we can split the parallelism methods into two kinds, data parallelism and tensor parallelism. For data parallelism, it's about parallelism the data in practice. So you can see on the left, we can split our data sets into two batches. This sampling will be done IID. We give one sample to the device A, which holds the whole model. One other sample to device B. We also hold the same replica, the same copy of the same parameters. That's data parallelism in order to ingest bigger batch size or more data, given that you have more GPU. Tensor parallelism, on the other hand, is not about parallelism, the data, but actually the model. Sometimes the model is so big that it cannot actually fit a single device. So that's usually the case. If you go between dozen of 100 or more billion of parameters, you cannot actually fit it into any kind of devices, even the highest grade of a GPU or TPU. For that, you need to do a parallelism. Tensor parallelism is basically taking each matrix multiplication of your LLM and splitting the matrix multiplication across multiple devices. And it allows you actually to fit any kind of model, whatever its size, as long as you have enough devices. There is, for both of them, a lot of communication. For the first one, data parallelism, there is an all-reduced gradient at the very end of the forward needed to synchronize the two or more replica at every steps. For tensor parallelism, it's even worse. At every matrix multiplication, you actually need to do a reduce scatter and an all reduce of all your activation, meaning that it's actually very costly. Right now, that's basically what everyone is using, both in open source and in the big labs. The problem is that it needs communication at every training steps or multiple communication at every steps, which is probably fine when you have everything in a single data centers. But if you were actually to scale to non-collocated devices, for example, across different data centers, different cities, different countries, different continents, there it's much harder because actually the communication is going to be so huge that maybe you will have a overhead of communication time that could be 20%, 50% or more of your whole training, meaning that you're actually wasting a lot of your GPU hours on just communicating, which is really not what you want to do. For that, we need a low communication distributed training. A solution to do that is simply to communicate less often. But when I say communicating less often, it means that basically each model, each replica, will need to do some independent optimization. So that's the whole gist of federated learning that you may be familiar, that we take a lot of inspiration from it, but use it in a slightly different context. So you can see here, for example, an image. We could start from a pre-trained model or a randomly initialized model. We will duplicate the model into multiple versions. We will train them independently for a certain amount of steps, and then we will make a communication. So, for example, in data parallelism, it will be this all reduce that synchronize all the replica, and then we do it again. The difference here between data replica is that we can actually do an independent optimization for multiple steps, while for data replica, it's at every steps the communication is needed. This, because it will allow us to actually do cross-country distributed training. We still need to communicate as much data as DP, data parallel, when we communicate, but because we communicate only every 25, 50, 100 steps, basically we can amortize that communication cost across the whole training, meaning that we can actually work with replica on very different locations, even if the communication cost is very high, which also means that we could use different kind of hardware type. Because in that case, the communication cost is very high. We can also, and we don't need like a very tight synchronization, we could work with different kind of hardware for different locations. You will need to adjust, of course, the compute according to the type. So for example, we know that, for example, B100 is slower than A100, meaning that we probably will need to have like a bit more V100 to go close to or as fast as the A100. You could also do simply less steps on devices that are less powerful. That could also work. So what is the recipe? How can we actually make it work? Because it's not simply we communicate the gradients, this won't work. We need some kind of recipe. So this recipe, that is very close to local AGD, FedOPT, and is basically the root of our algorithm DiLoCo. We need to start from an existing model or random model. We need to have K worker across the world, and we assign a data shard to each worker that can be IID or not. And in that case, we need two optimizers, the inner optimizer and the outer optimizer. So for every round of communication that we call an outer steps, we're going to train workers in parallel independently without any communication. So for example, you can see here, we start from a model in gray, and then we do two kind of replica that each are optimized for the same amount of steps, but they may diverge in the parameter space in blue and in yellow. And for that, we sample a batch from its own data shard. We compute the loss, we can compute the gradients independently without communication, and we do independently an inner optimization with our inner optimizer. That could be, for example, Adam. Afterward, we compute an outer gradient. So I'm calling outer gradients, but that's an abuse of a language. It's not actually a gradient. It's more akin to a trajectory in the parameter space, which is basically a delta, a difference in a parameter space between the original model initialized at the beginning of a communication round and the new model. So this delta simply shows the trajectory that was spent for each replica across the independent optimization. We can consider this outer gradient kind of as actually a gradient, and we can apply it an optimizer. In that case, if your outer optimizer is, for example, SGD with a learning rate equal to 1, that's simply equivalent to do a model averaging. So, for example, like fed average, but also quite similar to the souping literature, where we simply average the two parameters. It's actually not very useful because usually you have low performance because of that.
How different this approach from federated learning?
It's actually very close. The algorithm here is literally the same algorithm for all these models. The difference is in federated learning, in most of the situation, for the inner optimizer, they only use SGD. For the outer optimizer, they use an outer optimizer that's quite more complex usually, for example, Adam in FedOPT. And the number of workers is usually very high, while in that case, no. But it's basically close to federated learning.
Other questions we can discuss after this, right? So to not interrupt your flow.
But yeah, basically, federated learning, distributed learning, local SGD, which is sometimes not always the same kind of literature, and DiLoCo is all the same field. I will say that the only difference is in which application is it. Also, federated learning, a lot of application is toward privacy, but here it's not the concern of this algorithm. But yes, that's very close to federated learning. To speed up the training, we can actually use another auto optimizer, SGD with a Nesterov momentum. So this is something we found in DiLoCo that actually what we didn't find in the literature before, is actually using a more complex inner optimizer like Adam, and then a simpler auto optimizer, which is particularly Nesterov, is actually a very powerful combination that actually was not found or not published in the literature before us. And we found that it actually speed up the training, meaning that we can train independently with this DiLoCo algorithm, but also get better performance for the same amount of lobs. So this is DiLoCo, our low communication distributed training optimizer that we published before. This is not exactly what we want, because now we have a communication efficient data parallelism method where we distribute data across replica, but we don't have a new kind of model parallelism in a way, because in that situation, in DiLoCo, we still require that each replica should be able to fit your device or your amount of device. So of course, in DiLoCo, each replica here could use internally model parallelism during its inner optimization. However, we still need to be able to fit everything. And if your model is huge, for example, if you have, let's say, a GPT-5 or whatever, you cannot probably fit it into a single university cluster that is not big enough. Therefore, we need also to invent a new communication efficient model parallelism method. The two main methods for model parallelism in particular are tensor parallelism and pipeline parallelism. So tensor parallelism, I talked about it before, and it requires a tight synchronization. So we cannot use that. Pipeline parallelism is a bit more flexible in a sense that you actually need different devices that don't need to be in the same location, they don't need to be collocated. And then you do a forward through the first device that holds the first few layers, and then you transmit the activation to another device that holds the next layers and everything. The big problem of pipeline parallelism is what we call the bubble of time. The bubble of time, and when you do the forward and the backward, there's actually a lot of devices that actually not use, and meaning that there is a low compute efficiency of your devices. We need, therefore, to find a new kind of architectures distributed by definition. Instead of trying to find a new algorithm of training given your current transformer, you can actually do the reverse and modify your own architectures to fit the distributed training method. And that's the gist of DiPaCo. In DiPaCo, we propose to use DiLoCo, the method, but instead of simply communicating all the parameters between all the replica, we do something different. We synchronize a subset of the parameters with a subset of the path to produce a modular network. So, and in that case, our modular networks could be several hundred or thousand of a billion of parameters, but it will actually never be materialized on a single location for both training and testing, because we will only hold at a given location a single path, which is a subset of the model across the whole depth. And a module, in that case, can be a single layer or multiple transformer block. It's quite flexible. So in practice, what does it look like? You can see that in our modular architectures, we could have a path. So on the right, you can see the figure that I showed before, for example, for DiLoCo. A path with 3 layers, let's say, 1, 2A, and 3B. But in that case, this one could also be seen on the middle as a mixture of experts. Indeed, if I, for example, for the second layer, I synchronize the second layer to A between the first and the second path, it means that actually they are synchronized, not tightly synchronized at every steps, but still they are synchronized, and it makes emerge implicitly a modularity of the mixture of experts that is actually never materialized on a single location. So what does it mean at test time? It means like our training time, our model look like this, but it's never materialized. So it's some kind of mixture. But at test time, we can only select a single path, which is a submodel across the whole depth of it, which also is going to be much smaller and much more efficient. So in practice, for our training, we choose to initialize our modular networks from pre-trained dense model for simplicity, and we choose to train it for as many steps as a 1 billion model counterpart. So this 1 billion model is a dense model, very classical, with feed-forward and transformer, and very classical. We did use more compute in that case for DiPaCo, but as a proof of concept, we show that our modular networks, which was 20 billion parameters, so 20 times more, managed to get like very close performance here. It was much more heavy and much more parameters, but the big difference is at test time, we never actually activate 20 billion parameters, but only 150 million parameters, meaning it's much more efficient at test time in inference. We wanted to get also much better performance and reach those performance. So we reuse the method that I've showed before, where we do the frequent gating, where at test time, we switch a path every X token to improve the performance. And we found that we were working first with a second slant of 1000. So that was our base performance of our model when we select only one path. But if we allow ourselves to interleave multiple paths, although note that here, each chunk is only forwarded by each chunk is a group of tokens, is only used by a single small path or 150 million parameters. If we gate, for example, if we regate every 128 tokens, we manage to get the performance of a 1B model with only using path of 150 million parameters, being much faster. DiPaCo, I just want to emphasize that right now, it's not very flop efficient. We did use more flops. We scale it up to the performance of a 1B dense model. It's not yet the complete revolution that is going to completely change the architectures, and I'm not telling you should stop doing model parallelism, data parallelism, or pipeline, or whatever. It's not yet the solution, but it's a step forward where instead of trying to find new distributed algorithm to fit our current architecture, what I want to advocate is that maybe we should actually switch the problem and change our architectures in order to fit better distributed system. Yes, so in the paper, we did explore a different kind of total number of paths. So here, we don't have properly expert as in the mixture of experts. We call it path, it's slightly different. As an expert is only a single block, or FFN, while an expert path is a whole model from input to output. In that case, we did try a different version. I think in the paper, we report version probably 16, 64, and 256 path. We did have an improvement every time we actually increased the number of paths, and we did find specialization like this.
I see a question from Pierre. Do you consider the weight averaging with worker speed or SIM tokens?
Yes, so we did kind of that's a good question. In our main experiments, we did try actually like multiple kind of devices across the world, but we didn't actually try to ponderate the speed, so it was inefficient. We didn't try asynchronous. In practice, we should have asynchronous communication, as we found in a later paper in asynchronous DiLoCo. We didn't find that. I didn't use that at all in DiPaCo, but we did try some kind of ponderation. So when you do the clustering with k-means, you never have actually like a completely uniform clustering where there is as much data on each clusters, and it's actually not a desirable features. So you may have some kind of cluster that are very specialized and that will be maybe much smaller than the others. So indeed, what we did is like when you average with DiPaCo, when you average your outer gradients, we only we weighted by the amount of data that was present in the clusters. So not the SIM tokens, but the prior that we have on the distribution based on the amount of data. What if you synchronize the different part of the model between workers at different epoch? I think we did try some ablation like this that we don't publish. So of course, if your model is not at the same location in practice during the training, so let's say you have one path that did like 10 epochs, and you synchronize a subset of this path with a subset of another path that did like 5 epochs, so not the same thing. in practice, it doesn't work very well. It's very depend also the gap in the training between the two synchronization agent, and also how late or early they are in training. If they are very late, that will be fine. If they are very early, that will be quite harmful. But in practice, that's not a problem that can be solved out of the box Niraj. And I think you should develop maybe some ponderation method to give more importance to the later methods, to the methods that are like more advanced in epochs versus than the others. So the handling of multiple optimizer per shard, we still have to assume a slight increase in memory per machine to hold the optimizer. It's not entirely true, because yes, we have multiple optimizers. We have multiple optimizer per shard. So we have the inner optimizer, Adam, and the outer, which is Nesterov. However, we can find a lot of optimization for that. So first, Adam gonna use a mu and nu, so twice the amount of parameters. Nesterov is only sometimes trace, so it's only one amount of parameters. First of all, you can probably, because you don't use often those outer optimizer, you could offload it on the CPU memory and only reload it when you need it. So that's very doable. You can also downcast it to much lower value, so accumulate it in B float 16, for example, those states, and then recast it in float 32 when you do the accumulation, which allow you to reduce a lot of memory. So there is all this kind of engineering optimization that you can do that we actually do in practice to fit and that work well. And furthermore, for each shard, so you have, like, as you said, the inner optimizer and the outer optimizer, but only for a path that by definition in our model is quite small. So here our path is 150 million parameters, which is nowadays a relatively very small LLM, despite the whole architecture being much bigger. So this itself is decentralized across smaller local amount of parameters. So I don't think Aaron is that much of a problem.
In the last bit of your presentation, you raised kind of an important question, which is like basically if we can, like, if we think about the capabilities of those kind of distributed compute clusters, what kind of architecture should we train on that? Maybe we can design like a better architecture. And DiPaCo can be seen as kind of proposing a slightly different variant of mixture of experts architecture. So I was wondering if you tested or like inquired into how does this type of mixture of experts like model compare to others like Switch or G-Shard or like, so did you explore that? Do you know maybe of someone else who explored that?
No, so I don't know real comparison because I feel like DiPaCo there's no paper that looks similar in the literature, so unfortunately. We didn't compare directly against MOE. So we know that MOE are in practice like much more efficient than us. So they're also like much harder to distribute because of the tight synchronization. I think a big caveat is in our system, we do a sequence routing. So we route the whole sequence instead of doing a per token routing as a mixture of experts. And actually, it's actually much better to route per tokens. It allows you also to have a proper knowledge sharing because you do it at multiple times and you really combine the knowledge. While in our situation, we do our frequent getting at test time, but it's quite imperfect. Harder to scale to as many paths as a mixture of experts, because a mixture of experts, you can see that every time you choose an expert in the online router across all the routers, it's actually taking a path, and there is million of paths. So it's actually much more efficient with current mixture of experts. However, it's harder to distribute. So our objective is to bridge the gap of efficiency of course routing or whatever variant with DiPaCo toward the mixture of experts, while be able to retain most of the distributed capabilities.
Another kind of somewhat related thing that you mentioned earlier in the talk is basically it comes out as a derivative of some of the things you said. So if you're training on a cluster with heterogeneous compute capabilities with a mixture of experts models, it may turn out that different, like imagine you have two workers, just in this trivial case, and one worker is substantially slower than the other, or like the other is substantially faster. If you're doing mixture of experts models, one kind of potential caveat is that might lead to, if the two workers host different experts and the experts hosted on like the slower worker happen to be like learned or initialized so that they assign the role of maybe doing low or doing some specific interpretable roles, which is what mixture of experts often do. Mixture of expert models. It might happen that training in DiPaCo might change the speed at which you learn those functions. So like what I'm a bit like, the context of the question is, unless in similar systems, unless you take specific actions, it might happen that the slower workers versus the faster workers actually make the model learn some functions more slowly, and this changes the training dynamics. Question: is this the case with DiPaCo? If not, how do you establish that the training dynamics are the same as though in centralized training? If it is the case, are there any ways to mitigate this, or should we embrace this, or like, what's your stance on this? Sorry,
No, that's an excellent question, and I think that's also open question. So basically, what you're wondering is like what we call in federated learning the laggard problem, when there's always like one that is lagging compared to the others. In DiPaCo, we are doing distributed training that's synchronous, meaning that we synchronize not often, contrary to DP, but when we synchronize, we are waiting for everyone, and they all need to be blocking. So in that case, in DiPaCo, we don't have that problem of laggard because we have to wait even if someone is slower than the others, which is of course like a default of DiPaCo that we would like to fix in later version. We did in another paper an asynchronous version of DiLoCo, where we actually like work on different kind of device at different speed, and we did have to find like methods to fix that. So in practice, we were applying the outer momentum for every replica as soon as they arrive in the synchronization point, so not at the same time, but we are not updating this outer momentum, so this value, at every steps, and we're actually waiting with some kind of buffer. That work in practice very well for DiLoCo at very smaller scale. It's unclear yet if it will work for DiPaCo. We didn't try.
Very small kind of follow-up based on, like, since this is synchronous, and I imagine that there is kind of some way to distribute the kind of model parameters between the workers, or like just initialize everyone. Is there any parameter replication and any need to synchronize the gradients at all, or is there no need? Sorry, it might be very naive, but I just need like a more direct answer to be sure.
I'm not sure we actually need the gradients. These outer gradient trajectories may actually be better, in my opinion. We did find that, for example, the less you in optimization, so the infinite optimization, let's say you reduce the number of inner steps close to 1, you will be much more similar to what is a gradient. In practice, we found it actually worse. So sometimes communicating independently for longer is actually better. So, which is maybe not intuitive, but meaning that we don't want to synchronize too often, even for the pure ML performance. It's not very clear in the literature why. One hypothesis is maybe that it can actually smooth the whole training, meaning that during the training, you have a lot of noise from each batch, but then when you compute the trajectory, which is like a delta in the parameter space across a lot of steps, you may actually smooth this noise that may be harmful and only keep a general direction that is easier to generalize from. But that's unwavy intuition. I don't think anyone knows for sure this.
I see a question from Maxime. Should we expect that a mixture of paths will be used to scale models to hundreds of trillions of parameters?
Yes. So engineering-wise, Maxime, I can say for sure that engineering-wise, we know how to make a mixture of experts scale to thousands of paths or more, and which will be trillion of parameters. Which is cool with the DiPaCo is, as I say, like we have this notion of path, but you could actually have much more path that you train at the time, and you could actually sample every time only a subsample of the path. So engineering-wise, we know how to do it at close to infinite scale. No, right now, the problem with DiPaCo, of course, is that as you scale, can you also get good ML performance? And that's still an open question.
What is the challenge then? Like, what are the blockers right now?
The blockers is to make the model much more efficient as you put more compute, so flop efficient. We are actually doing spending more flops because we train multiple small paths, but a lot of them in parallel to reach the performance of a 1 billion model. Ideally, we would like to spend less flops, less compute, or less time into it in order to have better performance. So that's purely improving the ML performance. While I think on the distributed side, we are already way ahead from the existing literature.
I really loved your recent tweet about more how did you say, like, compute is addictive, more you get, more you want?
That's the lesson, yes.
Yeah. So basically, if there's a more compute, we see the performance. But as I understood from your answer, you guys thinking how to improve performance without increasing computation, right?
Yes, yes. There is, I think, like a trade-off. And right now, given like enough GPU, you can fit all the GPU in the single data centers, and you will get good performance. DiLoCo will be only useful when actually you want to go one level above, when you cannot fit everything in a single location. And for that, it's only a certain amount of flops that actually interesting. And in that case, we are not yet as good as the performance you will expect. Meaning that we could get probably as good performance, but you will need probably to use maybe 10 times or 100 times more GPU than if you were able to collocate everything, which is quite annoying.
How do you guys decide the optimal path?
So in practice, what we do first a clustering. So we clustering K-means classic. We cluster, for example, in 256 paths. We associate to each independently some path, meaning that no, we have connection between the path, but that doesn't make any sense because there is no proper correlation between the cluster 1, cluster 2, cluster 3, or K-means. We train them for like close to 1 or 2,000 steps, so very little amount of steps. Then for all the path, we go on a validation set, we extract the scores, and then we train a small linear regression, a linear logistic regression to just find like which is actually for that path, that token, it should take that path, and etc. And then we can find some kind of ranking and make the optimal path structure emerge naturally. In practice, we only do this logistic regression classification of the path only once. We saw, and I think we show in the appendix of the paper, that if you do it 2 times, 3 times, 4 times, you can further improve the performance, of course, with diminishing results.
Is performance improving like significantly, or just like very slight improvements? So
the first one is a big improvement. I think we have a table in the paper. It's probably like 10 or 20% improvement. But then after the second time you do this kind of reclassification of the path, or the third time, you get much less improvement, which is, I guess, quite expected.
What hardware do you use for training?
We did proof of concepts to prove that we could actually use different kind of hardware. So we did try different kind of GPU, V100, A100, and different kind of TPU. But in practice, for the main experiments, we are using A100.
I just want to try to make sure I'm understanding it correctly. So mine's meant to be a clarification. But I guess my interpretation is that you, through your clustering and those techniques, you identify the entire path through the network in advance based only on the input data, which is a little bit different than a mixture of experts, where each layer is looking at the intermediate activations to compute the route through the next layer. So first thing I want to know if that interpretation is correct, that part, if I'm interpreting it.
That's correct for the first step, as I said to Sophia. So the first step is just K-means clustering, you give 2 paths, but then we do a reclustering afterward with a logistic regression.
The reclustering happens in an intermediate layer, or?
No, so the reclustering basically, so you do first clustering with K-means, you train 64 paths. They are combined together, but in a suboptimal way. That doesn't really make sense. Then for each, you extract all the logits on the validation sets. And for each of them tokens, you can know like what is the loss per token. So now you have like basically loss per token. You can find then among all the loss per token, which path will actually be optimal on that validation set on that token. So you use the big matrix, basically. You take a logistic regression on it to do simple classification problem, among, for example, 64 paths. And then you can find, actually, this token should have gone there, And now you can use this logistic regression that take input and embedding. So we just associate each token as token embedding. And this logistic regression that can reclassify seconds to this. So here I'm doing per token, but actually we do it in practice on a prefix, so a group of tokens that average the values, and we route the whole sequence. So it allows you to recluster, to kind of way like to clean the bad initial clustering of the K-means to a new clustering. And we found in practice that it allows you to know the right combination by doing so. Does that make sense?
I'm just worrying whether my preconceived notions are tainting my interpretation of what you're saying. But I think I do understand that you're taking your signal from input token to output token. You have a combinatorial number of paths in there.
Yes.
you know, so it's but you are in fact choosing that combination of choice points.
So we can simplify the problem a bit with a product, because if we consider that, let's say that we have two levels. So in example, in figures, maybe I can show the figures. Here, for example, like we have three levels, but because the first layer is synchronous for everyone, let's say we just have two levels. And because these levels are tightly shared, so we know that, for example, 2A is the same between 1 and 2. We can know that basically the optimal token should have taken the let's say like the optimal sequence, let's say, should have went to the path 2, meaning that we know that basically its optimal module will have been 2A, those two, and 3B. So basically, we know we don't do one classification, we do actually two classification, one per level for each of those levels. So it simplifies a lot of problem, and then you simply do the product of your classification results. And actually, you two levels, but you can do it for 3-4 layers. So it's actually to scale more easily to this problem of combinatorial that you indeed notice.
But you are in fact choosing the path that the node at layer 10 based on the embedding at layer 1.
Yes.
Yeah. So that's interesting.
No. The embedding we use.
Okay.
For the embedding, so like the embedding that we use like a very small model on the side that just extract the embedding of the prefix. That's it.
Did you also talk about how you solve the pipeline parallelism, because you're still basically going through many steps of a pipeline with any given path, right?
No, that's not true. So that's one thing. We don't want to do pipelining. Basically, like if you say like 1 to 128 to 3A, literally it's just a small model of like the whole thing is like only a small model of 150 model parameters that you can fit using, if you want, transfer parallelism or data parallelism, but on a single small amount of GPU co-located, and you don't need to do pipelining.
You have this combinatorial number of paths though, but you're going to say one of my nodes for this batch is going to configure this path, and then it's going to process for this path, and then the next batch might pick a different path, and so you might have.
So we pre-shard the data. The data is pre-shard beforehand, and then you have like as much data set as you have path. So there is no like one path go there, one path go there. It's already done beforehand.
So does that mean during training you're going to have a finite number of paths? Something much less than the combinatorial number that you're ever going to go through during the training? So like let's say you had two possible paths at each layer and you had 10 layers. There'd be 1,024 paths, right? So in
that case, like first a module, like for example 2A, 3A is not necessarily one layers. It actually can be in practice like it's a lot more layers. Here, I think we did like close to half of the network was one module, the other half of the network one module. So there's much less combinatorial. So for example, I told you that the biggest model we trained, it was like, for example, in the paper, it was 256 paths. So that's much less. And I just want to note also that in practice, we had some experiments where we could actually have much more paths, so like thousands of paths, but you don't need to actually materialize all the paths. And some of them you could not train, meaning that some modules will be shared with less path than others. And that could also work. And that's also, I think, a future direction that will be interesting, to have a number of paths that is huge, but you don't need to have them all materialize at the same time. And maybe you could just sample from time to time new path.
That little fact there actually made a lot of things click for me. Okay,
I should explain it better.
Got it. Okay.
Do you restart or resume the momentum buffer of the inner adaptive optimizer? That's a good question. In practice, we resume the values of the mu and the nu of the inner optimizer. We did try to reinitialize it or to communicate it. Communicated it makes barely any difference. It's barely improved the results, while actually mean you communicate much more data. So that's not very desirable. Restarting those inner buffer is actually quite harmful in practice. So the best way is simply to not communicate it, the inner momentums of the inner optimizer, and just leave them across different phases. Let them resume.
What you're like with this work and with DiLoCo, if you really zoom out, it can be seen as like an alternative to the way people traditionally train, for instance, LLMs. Okay, let's focus on LLMs as like going decentralized versus going centralized. And if you like the way you write the motivation, the introduction sections there is like the main selling point is that you can reuse the hardware that's already there, the preemptible hardware, the existing hardware in different locations without like having to build. But imagine the other kind of potential application, and please kind of estimate for me the perspectives of the DiPaCo, DiLoCo based methods. Imagine you want to train like the very large LLM, the mother of all LLMs. You want to train something at as large scale as humanly possible. You can measure it in gigawatts and flops and whatever you want. There you have essentially two strategies for doing it. Either you can do everything very centralized, including like a lot of electricity centralized, a lot of heat dissipation in a centralized environment, all the networking with like growing scale. And on the other hand, you can start from scratch by just creating a lot of conventional scale data centers and running a DiPaCo-like potentially enhanced infrastructure there. The question is about which of those approaches scales better from the economic point of view. So if you take into account like the electricity, the heat, the administration, etc., what approach, like, is there any reason why one either centralized or decentralized approach scales better? Or is it undecided, or is it up to like, what's your point of view here? Does it even make sense what I've asked?
I just want to note, I think it's out of my expertise. So like, don't trust my answer fully. I do think that right now the problem may be that if you want to put everything in a single data centers, there is a big problem probably in terms of electricity. I can see that you may not have enough power plant, and you will need to build a whole power plant for that. And maybe in a region where actually there's also like some kind of initial cost. You already have like big data centers, so you're just going to build more, increase that existing data centers in a region maybe where there is not much capability for like hydro or solar power that could also be useful, or actually in a region where it's harder to build more nuclear power, so it's harder to scale. So there is a cost for that, both a cost of time that maybe you could actually switch and move your whole data center in a better region, while actually in DiPaCo you could simply base each shard of your model in different locations where it's the most advantageous in terms of energy, in terms of infrastructure and everything. You could also, I guess, imagine some arbitrage. Let's say I'm a guy that don't own data centers, but I own training for models. I have a lot of bugs and I'm able to run huge data centers. And basically, I can try to run right now data center in California, data center in Canada. But then there is someone else, for example, in France, that tell me, oh, but actually you can get my data center for a bit cheaper during that month and that month, because we know we will have less usage. And I'm saying, okay, great. But then during my training on the fly, I can switch part of the training in other data centers. So as an actor training my model, I could do some arbitrage of the data centers on the fly. That would be much more advantageous.
Question from me. Just wondering, how do you see the further development of DiPaCo? Like, what are next steps? What you're planning to work? How to develop further this project? So
I'm still working on this kind of field. I think distributed is the future, and it's something that is not yet explored enough at scale that I want to push. Right now, one of my big concerns is how to make it. We're already like very distributed, efficient in terms of communication. My real concern is how to make it more efficient, ML-wise, to get better performance for the same amount of flops you put in.